All right, so 3.2 is on continuity, intermediate value theorem, and behavior. Okay, so as I said before, most calculators like to draw graphs that are connected. Older calculators actually had problems with graphs that were not connected. Okay, they wouldn't always draw them correctly. Our calculators do a little bit better job drawing graphs that you kind of have to like lift your pencil up and put it back down to keep drawing. Okay, here's an example of a graph that you can't draw without lifting your pencil. Let's say 2 divided by x plus 3. You can't plug -3 in for x. So when you try to draw this graph, you get one piece, and then you get a separate piece. That type of graph is not continuous because you would draw one piece, you lift up your pencil, you put it back down, and you draw the second piece. Those two pieces are not connected in any way. Old calculators would try to draw it like this.
A line in between.
Where it would try to connect it, but that connection shouldn't be there. Okay? Our calculators, as long as you keep it set the way it already is probably set, it draws it a little slower, but it draws it more accurate. That's how it should look. So is that exactly the one I just did? I think I did x plus 3. It's the same idea. When you're asking if a graph is continuous, you're basically saying, can you trace forever on the graph without lifting your pencil? If the answer is yes, then the graph you just drew is what we call continuous. If you have to lift your pencil, put it back down somewhere else, and keep drawing, it is not continuous. That's not continuous. Okay. Here's another one. This one is called the integer function.
There is a way of pretty sure making them all always continuous.
And the integer function basically rounds numbers to the nearest integer. It's kind of what it does. It rounds down. The point is, could you draw that graph I have on the screen without lifting your pencil? No, you'd have to lift it a bunch of times. That's an example of a graph that is not continuous because it rounds down. And there's nothing in between because integer means it's rounding. So there's gaps. So you have to lift your pencil when you draw it.
Wait, what was the equation?
I typed in integer. It's under math and then number.
That's right. Wait, what did you even?
It's option 5 under number.
You type in 5 and that.
Option 5 under number. It says int. How about this graph?
What did you type in?
So you're going to click on math, and then you're going to click the...
No, I have the video. I'll see what the accurate order. That's what after you put an integer, I'll just see.
Now, how about that? Is that continuous?
It appears to be.
Yeah, that's a parabola. You could trace the whole graph and draw it without lifting up your pencil. So the first two are not continuous, and the last one is. Learning which graphs are continuous and discontinuous is really just kind of practice. So what does it mean more formally? I mean, you can say, like, you don't lift your pencil, but that's not really a math definition. So if you want to describe what it means to be continuous a little bit more formally, you can describe it on an interval. So basically the idea is if you can go between one point and another point on an interval.
Is that the function f?
Yes. So if you can start at a point, stop at a point, and not have to lift your pencil, then that would be considered continuous. So if you had a graph like this, say something that looks like just a graph that was like in two different pieces for whatever reason. Let's say this is A and this is B. Could you trace between A and B without lifting your pencil.
Yes.
Yeah.
Yeah. So we could say that the graph is continuous on that section. Not the whole thing, but it is on that section. How about could you trace between C and D without lifting your pencil?
Yeah.
Sure. That's continuous on that section. Could you trace between B and C? No. You can't go from B to C without lifting your pencil. So usually when we talk about a graph being continuous, we talk about it in one of two ways. Is the whole thing continuous? Or can you find a section that's continuous? Depends on what you want to talk about. So if it meets the definition where you could start, and here, notice it says the word all. Oops. It says the word all. All means you can start anywhere and stop anywhere. So if they ask you if the entire function is continuous, as long as you can go from any starting point to any stopping point, that would be considered continuous. If you could pick a starting point and a stopping point where you have a gap somehow, then it's discontinuous.
What would a question like that look like?
Well, it might just ask, like, is the following function continuous or discontinuous?
Oh, okay.
And it would either be yes, it is, or no, it isn't.
Okay.
Right? If I ask you it like that, is the function continuous? I mean everywhere. I don't just mean can you find a small section. I mean the whole thing.
So when they say like function, it means the
Function means the whole thing. If I specifically said to you, is this picture continuous between A and B? Then you would say yes. If I said, is it continuous everywhere? You would say no. So this is the idea we just talked about in that picture. You can find a graph where it might be continuous on one section, but discontinuous on another. Let me draw another. I'm not going to do this problem, but I'm going to just draw a picture. Okay, so here's another picture. Here's A, B, C, D, E, F, G. Can you name me an interval that would be continuous on that graph? Just a section. Just a section. Yep.
Yeah.
Sure. E to F. So continuous interval would be from E to F. Now, do you want to include the E and the F? Not include the E and the F? It's up to you.
I'm sorry. Include the E and the F for it to be continuous?
I mean, you can write the interval however you want. Do you want to trace just between the E and the F?
Oh,
and
yes.
not include them?
So,
or do you want to include them?
So closed bracket on the E, and then open bracket on the F.
Okay.
You can do like a closed bracket, but because it appears that everything after F is continuous, I would put an open bracket.
You could do it any way you want. Open brackets or closed brackets, it doesn't really matter. You can trace from E right up to F. You can trace from E and go include F. I mean, either way, it's continuous. How about another interval that is continuous? Yep.
B to C.
And what kind of interval do you want to use there?
Just two open brackets.
Two open brackets? Sure. So now he's saying you can trace between B and C, not including B and C, and never lift your pencil? Yeah, I agree with that. That's fine. How about discontinuous? What would be an interval that is discontinuous here? Yep. Yeah, anything that goes from the left part to the right part. So D to E. Include the D and the E, don't include the D and the E, doesn't really matter. What would be one more interval that's discontinuous?
You could do anything like left of A. G?
So like from where to where?
I mean, like, there's not really a point, but anything before A and anything after G.
Well, okay, just to make that clear, we don't know what happens after A, really. So we'll just say it starts at A. Maybe it's continuous after A, maybe it's not. I didn't draw it, so we don't know.
From C to F.
Sure, C to F, open interval, closed interval. Basically, as long as you jump that gap, that's a discontinuous interval. Yep.
So the black dots are closed, so that means greater than or equal to.
Yeah, the black dots are just marking spots, really, on the line.
Okay.
Whether you use open intervals, closed intervals, the idea is if you can trace from here to somewhere else without lifting your pencil, it's continuous.
Okay, so how do you draw the open or closed intervals with respect to the graph? Like, how do you know which one's open and closed?
Well, I guess you could use an open circle if you wanted, or a closed circle.
Oh, so it doesn't really matter.
No.
Okay.
Again, don't think of these as open and closed circles here. Just think of them as, maybe I should have used tick marks. Tick mark E, D, C, and D. They're just marking a spot on the curve.
Okay.
Whether you want to include the spot or not include the spot when you trace between two of them, it doesn't really matter.
Okay.
Just think of them as, it's just marking a spot. So use tick marks. So there's 3 different ways that you can have a graph that's discontinuous. One of them is if you have an undefined value. An undefined value can happen when you have a fraction with a variable in the bottom. Is there, if I type this in, 1 divided by x plus 2, is there a value I can't plug in for x? Yep.
You can't plug in -2.
Can't plug in -2. So what that means is that -2, you have a discontinuity. And it's because -2 would cause you to divide by 0. And that is undefined. Can't do that. So that's one way you can have a discontinuity in your graph. Another way is not because you get an undefined value, but it's because there's like a break or a jump in the graph. So is there any number that you can think of that you can't round down? Like if you tried to round it down, you'd get error. Yeah?
0.
Well, I could round it down. I could just say it's like 0. I mean, it's just itself. It doesn't change when you round it, but you can still round 0 and just say 0.
You say infinity?
Well, infinity is not really a number, so we can't talk about rounding. That's a concept.
Yeah.
So we can't round concepts. We can only round numbers. Is there any number that cannot be rounded? Yeah?
I do it for, what is that? After the has a, what is that word?
Break.
I actually wanted to ask a kind of separate thing. Would pi, like the interval, the variable pi, do anything special for like these graphs? Like, is this like 3.14, like all that stuff, like repeating, like I don't know, would it do anything special for graphs, like special?
In terms of like rounding it?
No, just for like shape-wise, because you have the 2 graphs, like the one that never like touches each other, like the ones that's like this. Then you have the other one that's like the dashes.
Yeah.
So is there like a special like pie graph or something? Like not pie graph, but like a
Not really. I don't think so.
problem. Okay.
There's nothing with pi we're going to talk about in this section.
Okay.
Could you do like imaginary numbers, like square root of 2, or like?
Remember, we're talking about real numbers.
Oh.
So yeah, we haven't talked about anything with imaginary yet, so we're just going to stick with real numbers. So is there any real number that you can't round off?
No.
No. You can round off anything you want. So like, if you plug in 5 to this integer function, you would get 5. If you plug in 5.2, you would get 5. The integer function is just a function that rounds down. What if you plugged in 5.9? What would you get if you round down?
Oh, yeah.
5. It always rounds down. What if you plug in 6?
Yes, sir.
What about 6.5? 6. So you can plug in any number you want and round it off. The discontinuities in this graph are not because of undefined values. You can plug in any number. The discontinuities is because of the rounding. Right? When you round, you don't use decimals. So you either round to 2 or you round to 3 if you're rounding to the nearest integer. There's nothing between 2 and 3. There's a jump, okay, or there's a break. So that's breaks or jumps in a graph can also cause discontinuities. And the third thing that can cause discontinuity is a hole in the graph. Okay, the hole is the hardest one to see because if you graph it, you won't see it. The only way to know that a graph has a hole in it is to do algebra. So if we type in x squared plus 3x plus 2, and we type in divided by 2, x plus 2. Okay, if you graph that, like if somebody were to walk in and look at that right now, they'd probably say that that's some type of line y equals mx plus b. But it's not. That is not a continuous line. The calculator can't show you that there's a hole in the graph.
Even if you zoom in?
Even if you zoom in, you won't see it. The only way to see it is to factor the top. What do you get if you factor what's in the top?
You get 2 and 1, or positive 2 and 1.
X plus 2 and x plus 1. Yes. Now, what do you notice about what just happened when you factored in?
You cancel out the denominator and the x plus 2.
Right. It's like the x plus 2's cancel. Kind of.
You might be able to cancel them, but the rule of the beginning one would still apply.
Right. It was still there in the beginning. And if I graph x plus 1, it does look the same. The difference is there's a hole in this graph at a certain number, an infinitely small hole. So what number can you not plug into that?
-2.
-2. So what we really should do on the graph, if we were drawing it by hand, what does it look like? It kind of goes right above the origin like this. If you want to represent there being a hole at -2, so here's 0, -1, -2. What you really should do is this. Leave a hole there, put an open circle, and draw your graph like that. So that's how you show that there's a hole in a graph. And again, looking at the graph on the calculator, no matter how much you zoom in, it will not show you there's a hole. Because think about it. You can plug in -2.0000000001, and that'll be fine. You can plug in -1.99999999999. That's going to be fine. The only thing you can't plug in is -2. Okay, so finding a hole in a graph means you have to factor it and see if you have a common factor. That's when holes happen. Common factor between the top and the bottom. Now, if I mess the top up a little bit, let's make it so it doesn't factor into x plus 2, x plus 1. Change the plus 2 to a plus 3. Now the top doesn't factor. I messed it up. If you hit graph now, it's totally different. There's not a hole in the graph anymore because it's not going to factor into x plus 2, x plus 1 and have those cancel out. This is more like the first one, where now it's an undefined value that you can see. So a hole is an undefined value. It's just an undefined value you can't see. The first one is an undefined value that's very easy to see.
I'm sorry, can you go to the equations on the calculator?
Yeah.
symbol.
The divide by sign?
Yeah, okay, that's
No, that's just divided by, yeah.
just clear.
So just to kind of summarize, undefined value you can see very easily. Undefined value you can't see very easily because it's a small hole. And then a break in a graph that's also very easy to see. Yeah.
Why does it become the again like that one, like that graph, when you change it from x squared plus 3x plus 2 to x squared plus 3x plus 3?
Because the top doesn't factor anymore into something that would cancel with the bottom.
Okay.
The only time you get a hole is if you have factors canceling each other out. I think we said that yesterday. Every polynomial is continuous from negative infinity to infinity because we said the domain was what? Yeah?
All real numbers.
Yeah, a domain is all real numbers. So if I ask you to draw a parabola or a cubic or something like that, you can always draw it without lifting your pencil. Every single polynomial. You never have to lift your pencil. And if you never have to lift your pencil no matter where you draw it. Okay, we talked about maybe you could find a section that was continuous. But now what I'm saying is if you can draw from anywhere to anywhere without ever lifting your pencil, then that's called a continuous function. It means the whole thing is continuous. So every polynomial is a continuous function. I don't care where you start and where you stop. You'll never have to lift your pencil no matter what. And that's the idea of continuity. Any questions on that? Okay. So, intermediate value. How can I make this very simple? Let's say you had a pot of water, and the temperature of it was 70 degrees, room temperature. And you heat it all the way up to boil. As it goes from 70 degrees to 212 degrees, what temperatures will it hit between 70 and 212?
Between the 2 degrees.
Yeah, it starts at 70, you heat it to 212. What temperatures will it hit between those two values? Yeah?
All the numbers between them.
When you say all of the numbers, how many numbers are there between 70 and 212?
42. Oh, sorry, 212, 142.
More than that.
Infinite amount.
An infinite amount. So is there a time when the temperature is 80.3? 92.416? Yep. 107.4121915. Of course. The idea of intermediate value means that you hit every single possible value between two numbers. Now here's an example of something that this would not apply to. Let's say I count how many people in the room. 1, 2, 3, 4, 5, 6, all the way up to 20. When I went from 1 to 20, did I go through every single possible number between 1 and 20?
No.
No. I skipped 17.6, 19.4. I skipped a lot of numbers if I count from 1 to 20. So intermediate value theorem is the idea that you start at a number, you stop at a number, and you go through every value in between. You can also say it this way. Intermediate value theorem only applies to something that's continuous. That's why I gave you an example of like heating up water. That's continuous. You can't skip a temperature as you're heating water from 70 to 200 degrees. You can't. You can't go from 70 to 90. I mean, even if you put like a ton of heat on it at once, it doesn't just jump. It goes through all the temperatures. So if you're dealing with a function that is continuous between a and b, then it will go through every y value between f of a and f of b. It goes through every value in between. So let's look at a graph like this. Here's A. Here's B. So if I make a table of those 2 points. Here's the A value, whatever it's at, and here's the Y value. Well, I'd have to plug A into a formula to figure out what the Y value is. I don't know what it is. Here's B. And then you'd have some B value, or Y value, when you plug B into the formula. What the intermediate value theorem says is that you will go through every single value between that number and that number. So let's just say f of A, I'll make up a number. Let's say here's my axis. Let's say 1, 2, 3, 4, and 5. F of A, where does it look like the Y value is for A? Yeah? Looks like it's at 2. Where does it look like the Y value is for B? F of B. Yeah? 5. Is there a point in that graph where the Y value is 3? Of course, I hit 3 right there. Is there a point where I would hit 4? Is there a point where I would hit 4.2? Yeah, I'm going to hit every number between 2 and 5 on that graph. Is there a point where I'm going to hit 6? Well, no, because, yeah, 6 isn't between 2 and 5, right? But there's, 2.316. Yeah, it might be right there. You're going to hit every Y value between 2 and 5 on that graph. That's the idea of the intermediate value property. Now, let's say you had a function that wasn't continuous. Let's say it did something like this, and then it picks up again up here. And let's say this is at 0, and this is up at like 6. Am I guaranteed to hit every Y value between 0 and 6 in that graph? No, because it's not continuous. That's the whole point. It has to be connected. I never hit 2. I never hit 3. I never hit 2.5. There's a gap that I miss. So intermediate value theorem only works on a continuous function, and you're guaranteed to hit everything in the middle. What if I go from a positive value to a negative value? Going continuous. What's guaranteed to happen if you know that this is at a negative value? Let's just say -4. And this is at a positive value. Let's say positive 10. I am guaranteed what's going to happen. Yeah? I'm guaranteed I'm going to cross the x-axis, which means I will hit 0 somewhere. Yep. You're guaranteed you're going to hit 0 somewhere. There's no way to go from a negative to a positive without going through 0. I mean, you can try to avoid it, right? If you want to go from here to here, you can say, well, not going to go, not going to go, I'm not going to go. Well, eventually, you got to go, right? You're going to have to cross it at some point. So you're guaranteed to hit 0 if you go from a negative to a positive in a continuous function. Okay, so last thing. The last thing is what we call end behavior. And the end behavior is basically what a graph looks like on the left and the right side. So for example, a graph like this. We would describe the end behavior as up on the left, up on the right. A graph like this, we would describe it as down on the left, down on the right. A graph like that has one of each. It's going down on the left side, but it's going up on the right side. Now, if it does something like this, that's exactly the same end behavior as what's next to it. It does little twists and turns in the middle, but when we're talking about end behavior, all we care about is what's happening on the ends. Who cares if it turns in the middle? So, let's look at the graph of y equals x cubed. y equals x cubed. We type it in. There's two ways we can describe the end behavior. What would you say it's doing on the left side? Going down. And on the right side? Going up. So this is one way to describe it. The arrow that you put on the left side describes what's happening to the y values on the left. The value you put on the right side describes what's happening on the right side. So down, up is one way to write the end behavior. Yeah?
It feels like a square root function.
Well, a square root function, that's not a polynomial.
Oh.
And we're only talking, I guess I could add the word end behavior of polynomial functions.
Yeah.
So we're only talking about polynomials in this whole chapter. Now that is another way to describe the end behavior. Let me read it exactly and then I'll kind of simplify it. The way you pronounce that is the limit of f of x as x approaches infinity, or the limit of f of x as x approaches negative infinity. So what does that really mean? Well, this is describing something, and then this is describing something else. This says what's happening to the y value as x heads to really big numbers. So how would you answer that question? In this graph, what's happening to the y value as x gets bigger and bigger and bigger? Yeah.
It increases.
And what does it increase to?
It increases to infinity.
Yes. As you head further and further to the right, the y value gets bigger and bigger. Now the bottom one. What's happening to the y value as x heads into the negative numbers more and more? What's happening to the y value as x heads further and further into the negative numbers?
It's reaching negative infinity.
It's reaching negative infinity. Both ways are fun to describe end behavior. The limit notation is something you will use more in calculus. Drawing arrows that point up and down, nobody really does that a lot, but it's at least simple to understand. That's why I showed it to you first. So with polynomials, you really only have 4 types of end behavior. Up, up, okay, like a parabola, or down, down, like a parabola. Down, up, something like that. And up, down. Those are the four types of end behavior that you can have. Any question on those 4 types? So how do you know which type it's going to be? Well, it just depends on 2 things. If you've got something like this, all you have to do is look at the number that's in front and look at the highest exponent. If the highest exponent is an even number, it's going to look something like a parabola. Parabolas always have the same end behavior on each end. So do all even functions. Anything that has an even exponent will go up on the left, up on the right. Anything that has an even exponent with a negative in front will go down on the left and down on the right. So it all depends, is the first number positive or negative, and is the exponent even or odd? Those are the only 2 things that control the end behavior. You can add other stuff on here. none of that other stuff, none of that other stuff makes a difference. The only thing that matters for end behavior is the first term, the one with the highest exponent. That's what controls everything. Any question on that? Let me see. So that's the last page. So that term, that 3x squared, that's called the leading term. Maybe you already knew that. That term controls the whole polynomial. And that's what predicts the end behavior. And that term, is the first number positive or negative? And is the exponent even or odd? So positive, odd. If I graph this, it's going to look something like this. I don't know exactly how it's going to turn in the middle, but I know it's going to be down on the left and up on the right because of the 8 and 3. And this term right here, 8x cubed, that's called the end behavior model. So the leading term, I'm just going to put in parentheses, is called the end behavior model. So if I asked you for an end behavior model of this, you would just write 8x cubed. It's just the leading term. We can do another example of that if you want tomorrow. But that pretty much covers everything that was in that section. Okay, so our homework tonight, we were just going to do 3.2. So I know we finished up 3.1. We're going to hold off on that. We're just going to do 3.2 for the homework. Yeah, just 3.2. I'm not going to give you anything from 3.1.
Okay.
I'm going to put it on the board in a second. Just giving people a chance to copy.
It's just all the problems from 3.2 in the video.
Yeah, it's just going to be what's in the video. I was going to add some from 3.1, but just 3.2.
Alright.
Okay, what I'll do is I'll pause the video and I'll put a list of test topics in the video right now. Well, you guys are at lunch.